Good morning, students. In today's class, we just discuss about the what you can say the Miller indices and lattice planes. So here we're gonna see this schematic diagram. What is actually the lattice planes? Now, the lattice planes are nothing but the planes which can be drawn by joining the imaginary points. In the previous class, we have discussed about the um, distribution of atoms, molecules, and ions in the crystal. So we'll just call that particular thing as the crystal lattice. Here, what is happening when I just join this imaginary points with a line segment? So here we just say that when we join the line segment, right, uh, in three-dimensional view, so particularly, so we whatever the uh, structure we are getting, that structure is said to be planes. See, we're just thinking that the sets of planes in the lattice, each plane is set of parallel with respect to the another set of planes. You can just see the schematic diagram. So you can just draw infinite number of set of planes, right? Yes, here. This is one way, one set of plane, right? This set of plane is parallel to this set of plane. You can just see this. You can just we can have infinite number of set of planes. This is oblique line segments. These oblique line segments are considered to be the planes, and since that imaginary points are nothing but we call that imaginary points as the lattice points. So when I join these lattice points with a line segment, so I just call that particular thing as the lattice planes, right? So lattice planes can be infinite number of times. You can just draw infinite number of times. So here we can just see that I've drawn with when you see it very clearly. So the first part of this set of planes are in this particular format. So and the second set of lattice planes are the horizontal one, and the third set of planes are nothing but a vertical one. And the distance between these two planes, not any two planes, if either it may be this, or either it may be this, or either it may be this. So we'll just call that distance as nothing but interplanar spacing. In the later class section, we just discuss the interplanar spacing also. What is actually the interplanar spacing and how that interplanar spacing is can be known by means of a mathematical expression, right? So see, whatever we are imagining that is being proved, right, mathematically, that should be proved mathematically. So since we are imagining that the atoms, ions, and the molecules which are residing in the crystal are nothing but they are in a sequential order. So how we can say that is in a sequential order? By imagining these points, right? These points are nothing but it is designated as the what you can say sequential arrangement of the constituent particles which are residing in the crystal. So here what we'll discuss is that how these crystal planes have been formed and what is the importance of this crystal planes. What is the need of studying these crystal planes, right? So when we just move to this right crystal planes further, you can just see now the set of planes which is given the names, right? So is given they will just call mathematically these planes. You can just see this. These are the different sets of planes, and these sets of planes is given a name as Miller indices. In the later section, I will in detail I will tell you about Miller indices, right? So how this Miller indices has been designated, and how you can geometrically how we can find out this Miller indices. So first of all, what is the need of studying the crystal planes and what is the Miller indices? Is that see here in the crystal, as we say that the lattice points are the imaginary points, and these lattice points are nothing but the exact. uh, view of the residing of the constituent particles. So now that can be mathematically represented as HKL, and we just say that these planes are having more concentration of the constituent particles. So here we are interested in knowing the more number of atoms or molecules or the ions which are residing inside the crystal. Our aim is to find out where actually the constituent particles are located. So in order to locate that particular constituent particles, we have just designating the uh, points with the lines, and we just say that lines are nothing but the set of planes which can be drawn in oblique way, the horizontal and the vertical. We say that vertical planes, horizontal one set of planes HKL, and the you can just see in the previous figure also I have shown you how this set of planes look like, right, geometrically. So here, what is the interest of studying all these planes are nothing but we want to designate, we want to know exactly where the more concentration of the ions, atoms, or the molecules, we just say that these atoms, ions, and molecules are nothing but constituent particles, right? So, where actually they are located. So, in order to locate this more concentration of the constituent particles, we need to mathematically uh, we need to some we need to designate it mathematically. So Miller is a scientist who had designated these line segments as set of planes, and he just represented it with HKL. So we'll just have a very what you can say a detailed study regarding this Miller indices, right? So now, first of all, we need to understand. First of all, we need to understand the how we can locate this HKL planes. So first of all, we have to choose a unit cell, right? Choosing a cell, then what will be its origin, then how the axis of the cell, right, look like and represented. So that part we have to do in order to designate Miller indices, right? Now, so here we are just shown you. So this is the set of equidistance planes, lattice planes. So first of all, this is three-dimensional, right? So we can just see two-dimensionally. So this the what back side of this what you can say point, you get it plane also. So that is the reason that we have just written in this particular format. This is one set of unit cell. Then we have located an origin, and then we can just draw a set of plane. So now, choosing its cell origin and the axis, now we can just draw. You can see first we can just draw a set of planes of the nearest origin. See, I just told you that we have just designated this as an origin. So like that, you can just draw a set of plane, right? This is one. So you can just see this is called 1 comma 1 and infinity. I'll just tell you what that is actually look like. So you can just see this. This is the set of planes when the crystal is in the shape of cube. So you can just say these three lines, right? They are joined in the cube, and they are represented with x, y, and z. Either wise, right? This is x and this is y, and this will be z. X, y, and z. X, y, and z. See, the x, y, z is represented with the dark, right, black line, right? So here also, this is one of the set of plane. You can just say this. This is a set of lattice plane. This is the set of lattice plane, and this is the set of lattice plane, and this is also the set of lattice planes. Now, why it is called 001? You can just see A1, A2, and C are nothing but they are the lattice planes, right, with respect to x-axis, y-axis, and z-axis. How this is how I have written by seeing this cube, how I can write 001. You can see this part is see. So if this is uh, right, uh, this part you can just see this is the part, and we say that this part, see, I already told you this is x-axis, and this is represented as y-axis and z-axis. So z-axis is right, is completely this plane is completely cutting the z-axis at C. So we just write the plane which is parallel to the other two axes. This plane is, you can just say this plane is parallel to another other two axes. So we just represented the plane of the other two axes as infinity, and the reciprocal of it will give us give us the zeros. And see, we have written 0 0 and 1. I will just show. See, no problem if you have not understood. So that we in detail will just, I will tell you, explain you how I got 0 0 1. Now this is the representation of 0 1 1. You can just see this is infinity 1 1. You can just, when you see this figure, you will easily understand how. See, you can just see this figure, right? So this is the plane for which I have to locate the Miller indices, and this plane is cutting the y-axis and it is also cutting to the z-axis, but it is not cutting the x-axis, right? These x-axis a1, a2 and c are nothing but they are the intercepts with respect to x, y and z-axis, right? Whenever this plane is cutting a particular axis, we just say that that is considered to be 1 unit. So here the minimum value is, we just reason that we have just written it as 1 unit, right? So now 113, how I can just write this 113? You see, this is called 113. 3, why it is 3, right? You see this part, right? So cutting this part, x-axis, y-axis and z-axis. So this is entire, this entire portion is what, 1 unit, and this entire portion is another 1 unit. But at the z-axis, see, this is completely 1 unit. So 1/3 part is cutting by this particular plane. So I've just written it's 1 comma 1 comma 1/3. So you can just take its reciprocal and then we'll get this 113. Okay. So now likewise you can just draw different types of what you can say Miller indices. See this representation. Yeah, see, now this is yeah, this is also considered to be 110. I have shown you with the arrow mark, right? This is 110. You can see. Likewise, you will have numerous number of examples of this Miller indices, right? Okay. Now you can just see. Just see. We just have a very detailed understanding of this Miller indices, right? See. mm, See, Miller indices. See, first of all, in order to understand it very clearly, see, first of all, we just have a basic definition of this, right? Right. See, Miller indices, a very, what you can say, you can just see, everybody can see this, right? See, the points, direction, and the planes in the unit cell. Unit cell, just now we discussed that a smallest geometrical figure which can be drawn, right, in 3 dimension, right? It is a unit cell. Particularly with when you see 2 dimension, also you get a unit cell. But in we are talking about 3 dimension. So the smallest geometrical figure which can be drawn is known as the unit cell. So if you just know this unit cell, then you can just designate this Miller indices. You can just see uh, a small notation to describe certain crystallographic directions, right? See, these are nothing but, see, this represent the directions, right? So this type of representation, see, x-axis, y-axis, and z-axis. So you just say that is called crystallographic directions, right? And the planes, and what is this planes? I've just now I told you this is one set of plane, this is another set of plane, and this is another set of plane, right? Likewise, you have another set of planes backward, here another set of planes. Like this you'll have different set of planes. Now for example, if you get a negative number, that negative number should be represented with the bar, right? So now just I will discuss you about the crystallographic directions, right? So when we just see, directions in the crystals. How? So first of all, we just locate these directions in the crystal, right? So any line is specified by 2 points, right? Any line segment, you already know, that can be specified by 2 points, right? You can just see this is the line segment, this is another line segment, right? Likewise, you'll have a different line segment in the set of planes, right? This is one plane. See, I'm talking about this plane, right, which is shown in the figure. So any line which is represented with the 2 points, so which is represented by 2 points, typically at origin, right? Definitely, this plane will have, you have to choose an origin if you want to locate this directions or the lattice plane. So first of all, you need to choose the unit cell first, and then you have to choose the origin, and then you need to choose the axis. So now you can just see this. Now I've at this particular point is considered to be the origin, and now we just representing this see, and this a b c are nothing but they are vector projections, right, and small fractions with respect to each axis, the dimensions of the unit cell. So you can just see this see unit fractions a comma b comma c. So now see, this is one plane, and this is x-axis, this is y-axis, and this is your z-axis. This plane is not cutting, right? It is cutting at x and y-axis. You can just see, I already told you, this plane is cutting x here. See, it is cutting here, and also it is cutting here, right? So this is x-axis, and this is your y-axis, and it is parallel to the another axis, that is z-axis. So anything which is parallel to the z-axis will be taken as infinity, and reciprocal of it will give us the information of 0, right? So now directions with will help definitely the define the planes, or we just say that is called a Miller indices, right? Now, uh, right, this arrow marks represent the different directions. Examples I've given you. So now, so what is actually the crystal planes, right? So again, see, more in more detail, we'll just understand what is actually the meaning of crystal planes, right? So here we can just see everybody. So with a particular crystal lattice, it is possible to identify different sets of the planes, and these sets of the planes are equally spaced, and we say that when the planes are equally spaced, they are called the parallel planes. See, first of all, we need to understand what is crystal planes, right? So in theoretical aspect, it is nothing but a crystal lattice. uh, with the crystal lattice, the important the points, right? You can just identify a set of equally spaced parallel planes, right? I already told you that whenever the imaginary points are there, if I just draw a set of line segments, and we just say that when I join these lattice points, I will get a set of planes, right? So identifying this set of planes, and these planes are nothing but they are equally spaced, and we just say that lines are lattice planes. So in order to understand it more clearly, you can just see this. When first we just consider these planes, this is the points, right? Imaginary points, or we say that is lattice point. So here you can just see the distance between these 2 points are represented with the fraction a, and this distance between these 2 points is represented by the fraction b. Right now, everybody understood this aspect. I just say that this is a set of planes in 2 dimension. Now, what how you define this crystallographic planes, right? If the plane passes through the origin, so you have to construct another plane and create an origin, and then you can each axis decide whether the plane is intersecting or parallel to the axis. So how you define this crystallographic plane? How you just define it? So if the plane is passing through the origin, so either you need to construct another plane. First of all, it should be passed with the origin. See, my origin is here. This is my origin, and the plane is, this is my plane, this is my plane, right? So first of all, I need to choose the origin, and then see if the plane passes through the origin, so I need to construct another plane and create a new origin. Then for each axis, I have to decide whether the plane is intersecting. So the plane is intersecting here, so you can just see this is intersecting at the point x axis, and it is intersecting at the y axis. So here, creating a new origin, then each axis decide whether the plane is intersecting or it is parallel to the axis. Now, how we can just what is the procedure, right? In the You can just say that in PPS, you need an algorithm, you need a particular flow chart. So, in order to a particular protocol is followed, steps are followed to write a program. In the same way, here, what we are doing here is that in order to mathematically locate this Miller indices, first of all, we need to, what is the procedure to evaluate this Miller indices? What is Miller indices? So what is Miller indices actually? Miller indices are nothing but they how to evaluate that how to evaluate this Miller indices. So we need to Miller first of all, what is Miller indices? Miller indices are smallest geometrical ratio by right. It is the smallest geometrical ratio, and the reciprocal of these intercepts, which is of the of the concerned plane, right? Which are representing the x and y and z axes. So we just say that this particular smallest geometrical ratio has nothing but Miller indices, right? So what is the need of Miller indices? Miller indices help us to know the exact location or the concentration of the see exact concentration of the constituent particles. So what is the procedure to evaluate Miller indices? First of all, now the plane is ready, right? Our crystal plane is ready. So just now I told you our crystal plane is ready. This is your crystal plane in 2 dimension, right? This is in right. So here, how to evaluate this Miller indices, right? First of all, you need to locate the intercepts of the plane with respect to the concerned axis and in terms of A, B, and C, right? Write the what you can say the coefficient of A, B, C. So locate the intercepts of the plane, and if the plane is in terms of ABC, definitely it will in terms of ABC. So you need to write the coefficient of this ABC. Now take the reciprocal of this intercepts, whatever the coefficient of ABC you got, you have to take the reciprocal and you need to reduce it to a smallest possible integer. And now and then you just enclosed it within the bracket without commas. So that is a procedure to evaluate Miller indices. So here crystallographic planes are specified by 3 Miller indices, right? We say that these particular planes are nothing but they are designated with they are designated with HKL plane. We just say that 110 whatever here seeing, that is nothing but HKL planes, right? So here, so what is actually the meaning or definition, right? Just now we have studied about the Miller indices. So in the other way, the Miller indices is nothing but a vector representation for the orientation of this atomic planes in a given crystal lattice, and they are defined as the reciprocal of the fractional intercepts. And we just say with respect to the crystallographic axis, to find the Miller indices of the plane, we need to understand the what you can say. We need to take some following procedure determining the intercept of the planes along the three axes, along the three crystallographic directions. Right, take the reciprocals of the intersects and simplify it, right? So multiply each of the simplifying is what possible smallest possible integer, multiplying each of the denominator of the smallest fraction, and you have to take you have to take the LCM and just multiply it with the fraction whatever you got. Now you can just see this. If this is the plane, see, this is x-axis, y-axis, and z-axis, and this A, B, C are the smallest. They are the fractions, or we can just say that the dimensions of the unit cell along x, y, and z-axis. So this is the plane for which I need to evaluate the Miller indices. See, this is exactly cutting the x-axis. See, x-axis, the plane is cutting the x-axis at A, and this plane is cutting the y-axis at B, right? So now, so what I say that A, B, C, first of all, I'm locating the intercepts. So what are the intercepts? A, B, C. And this plane, you can just see the reciprocal intercepts is what? A is the, what is the coefficient of A? 1. What is the coefficient of B? 1. And this plane is not cutting the z axis, but this plane is parallel to the z-axis. So I have written it as infinity. When see, this is the rule of calculating the Miller indices, that whenever this plane is parallel to any of the axis, we just designate it with the infinity. Then what is the procedure to evaluate Miller indices? When you just got the intercepts, say I got the intercepts 1 1 infinity, now you just write its reciprocal, that is 1 by 1 1 by 1 and 1 by infinity, and reduce it to a fraction, that is 110. So whatever the value you got, that is called Miller indices, right? So this is the way how you can evaluate the Miller indices, right? Now you can just see this another example. This is one of the another plane. See, x-axis, y-axis, and z-axis. This plane again. See, this plane is cutting uh, the x-axis A here, right? B, and here this plane is not cutting the z-axis, but it is parallel to the see, this plane is cutting the x-axis, but it is not cutting the y-axis, but it is parallel to y-axis, and also it is parallel to z-axis. So, but the dimension, see here the distance between these. We have located this as an origin. This is origin, and this particular part is nothing but we have just this is the half. See, from here to here, we just say that is called one. This plane is cutting exactly at the middle, so we just write it the reciprocal, the intercept as 1 by 2, and this plane is parallel to y-axis and also z-axis. So if the plane is parallel to any of the axes, then we'll just represent it with infinity. So now the reciprocal of this is 1 by 1 by 2, 1 by infinity, and 1 by infinity, right? So you just simplify it, you'll get 200, and the Miller indices of this particular plane is considered to be the 200, right? This is one of the another example. You can see this is a cubic crystal is in the shape of a cube. Now this is the plane, right? You can just see this is a set of plane, right, which are intersecting at x, y, and z axes. You can just see that this distance between the origin to this particular point is taken as half here. Why? Because from here to here generally we'll just take it as one, right? Because it's exactly at the center, so we just take it as 1 by 2. You can understand this, right, very clearly when you just see this y-axis. See, this plane is cutting, see here, here. So here, the distance between from the origin to this particular point is taken as 1. And this part, see, it is greater than this one. So we just write it as 3 by 4, right? See, this particular complete distance is 1 unit, and this part, see, you can see this is I have taken it as 1 by 2, and this part is what I have taken it as 3 by 4. So 3 by 4, and the remaining is what? 1 by 4. 3 by 4 plus 1 by 4 will give me 1. The distance, you can just calculate the distance will be 1. So I understood everybody. So why it is 3 by 4? You just take it as a reciprocal, and when you take the reciprocal of this, you will obtain 2 1 4 by 3. Then take the LCM of 3, then you get the LCM of 3 here. LCM of this 2 by 1, 1 by 1, and 4 by 3. So 1 comma 3, LCM is 3. You just multiply it with this particular uh, value, whatever you got. 2 into 3 is 6, 3 into 1 is 3, and 4 by 3 into 3 is 4. So Miller indices of this particular plane, whatever you are seeing here, is coming to be 6, 3, and 4. So with this, you can just say that I've given you various examples. First of all, in today's class, we just discussed about the crystal planes, right? So why we need to understand these crystal planes? Because the crystal planes are nothing but they are consisted of a large concentration of constituent particles, right? Since we are geometrically we are assuming that the points, whatever the imaginary points are there, that are called, we call that as lattice points. And these lattice points, when I join these lattice points with the neighboring point, right? So either it may be 2 dimension or 3 dimension with a line segment. I just call that set of these line segments are nothing but crystal planes, and these crystal planes are nothing but we just say that is represented by the scientist Miller has represented it with the indices. So what is its Miller indices are nothing but HKL. We say that are HKL, and what is this HKL? The smallest possible uh, integer, right? Which has the same value as their reciprocal of this intercept of the concerned plane along the three crystallographic axes. So why we say that it's crystallographic axis? Since that axis we are represent designating in the crystal. So we just say that whatever the axis we are representing is crystallographic axis, right? So with this, we just stop the class for today's class. In tomorrow, next class, we'll just discuss the other aspect, right? Thank you, everyone. Thank you for your patience.